Okay, welcome to Information Theory Lecture 22. Let's see, today is going to be a very important lecture because we're going to, well, on the one hand we're going to finish our discussion of parallel channels and Gaussian channels, but more importantly, well, not really more importantly, about equally importantly, but this is still nonetheless an important lecture because we're going to begin our discussion of rate distortion theory. And today is the day that we will really, I think, spend most of the time on the intuition, although we will get to some equations too. So to remind everybody, please remember to read this and read that and read this and just read all of these things that are currently readings in our class. The other thing I want to mention is that I felt inspired this morning, and if you happen to notice, well, maybe if you looked at the lectures very early in the morning, you'll have noticed the lectures that said no homework. But then later in the morning, I said, oh, what a great opportunity. It's sunny outside, and it's a Wednesday. And I was about to say it's a Thursday because I'm so used to this class being on Thursday, but it was a Wednesday. And it is still a Wednesday, and I thought, what better day and time and moment to choose a couple of nice problems for homework. So I chose 4 problems, and these are really nice problems. I looked at a lot of problems, actually. There's only 4. So on the one hand, it's low in quantity, but high in quality. So they're actually really cool problems, actually. I think they're really fun. So 3 of them are on Gaussian channels, and one of them is sort of a network information theory-ish style problem, which is also good because it's going to get us at least beginning to think about the kinds of things that we'll be thinking about later on in the course. And then the last problem is a simple problem on rate distortion theory. And certainly by Monday the 27th at 11:45 p.m. we'll have had at least 2.5 lectures on rate distortion theory. So if anything, it's a little bit under representative of what we will know at that point. However, what one can do now is basically after today's lecture, you'll be able to do the first 3 problems. So I would strongly suggest, for one's own sort of synchronization sanity, that you do the first 3 problems this weekend because they were related to the Gaussian channel, and then next week wait till the 4th problem. Then you will be happy. And if you'll be happy, then I'll be happy. And if I'm happy, then you're happy. And then we'll get into this happiness feedback that will eventually explode with happiness all over the walls. And that's a good thing. At least it's a happy thing. Office hours, and that's old news. Okay, so let's do a little bit of review. So the paradigm that we are in at this point is that we have, again, multiple Gaussian channels. We have k of them. We have various different modifications or situations or modified paradigms to some extent. But the basic paradigm is the following: parallel Gaussian channels. In the one case, we have independence. So we have a diagonal covariance matrix, but we have a joint power constraint, which is that all the sums of the powers have to be equal to p. And then there's a colored noise, which is a modification here where the covariance matrix need not be diagonal. And we saw in the first case, when it was diagonal covariance matrix, that we had this form of capacity constraint. These are just different versions of the same equation. And then in the second case, when we had colored noise, we have this form, which is actually the same form, except that it's in a rotated space. And then to get back the powers, or the energies, the powers of the transmissions at each of the channels, we actually have to rotate the solution back using this form here. So we saw that last time. We also saw the stochastic case where we have not just colored noise, but we have sort of frequency-dependent noise, and we have a kernel function of some sort. And there, we didn't derive it, but we looked at this form of the solution, which is like a water filling-like argument, just like before. We discussed water filling last time, but here we have water filling in frequency domain. And where what we're filling is essentially, we're filling the valleys of the power spectrum of the noise. Okay, so that is, I think, a very intuitive property that I hope you find intuitive as well. Well, intuitive conditioned on knowing the water filling argument of the initial case. What we talked about last time and spent a lot of our time on, and in some sense what we're still talking about, is this case with feedback. So this is the more general model. So let's make sure that we understand this picture, this lovely picture. I spent many hours with a computer, with Adobe Illustrator, working on this picture to get the font looking like it was human generated. So so remember, raise your hand if this picture is perfectly clear. Okay, so it's not perfectly clear to everybody, so let's make sure. So we have these three different sections. The yellow section here, the green section, let's call this the light blue section. Hopefully you can see these things as well. And then let's have one more section, the orange section. Okay, so so the yellow section is just the noise, right? So we have multiple channels, we have n channel uses, but the noise is correlated, right? And so what this essentially means, this is the factorization structure of the noise, and this factorization structure corresponds to just the chain rule of probability. It's basically saying that if we were to write this out, what this picture is saying is really that P. This is a little bit too. Let me just decrease the width of this. P of Z1 to Z of n is equal to the product over I of P of Zi given Z1 to Z of I. Just the chain rule of probability. Right, and that's what basically this picture surrounded in yellow is saying. So it's just basically saying there's no assumptions. It's just a big, since everything's Gaussian, it's just a big joint Gaussian with a non-diagonal covariance matrix. Okay. The green corresponds to the received signals. You have n of them because we're using the channel n times. The blue corresponds to what was sent, right? So if we look at basically every time step, we want to send x1, it gets corrupted by noise z, and so we get y. Right. So then the next time step, we want to send x2, but x2 we get to use y1, and this is going to be corrupted by noise z2, and we get y2. And then next, we want to send x3, but x3 gets to look at what y1 and y2 was. And so it gets corrupted by z3, and so we receive y3 and so on and so forth. And they're all governed by the underlying message. So W, remember, is an integer index into which of the 2 to the nr messages we wish to send. And remember, R is the rate. And so when R is the rate, we're using some number of bits per channel use, and nr is the total number of messages, so we have 2 to the nr indices. Okay, does everybody understand this picture now? Yes. So this is our model of the feedback. This is just a model. Right? Remember, what a lot of information theory is now, and what it will be, is sort of like, well, what if the model is this? What's the capacity now? What if the model is this? What's the capacity now? What if the model is this? What's the capacity now? How about this model? What's the capacity? And so basically, at this time, people started saying, what about this model? What about this model? And basically, network information theory really is a whole class of models and a whole bunch of desirable capacity achievability results based on these classes of models. And basically, the research is trying to sort of push the forefront or the boundary of those models that we can actually understand from the information theory perspective of what's achievable, what are the capacities. So that's the game. I mean, basically, the game should, at this point, hopefully be very clear. Now, the actual details, of course, are where the devils lie. But the game itself is, overall, I think, well established, based on what we know at this point in this class. Okay, so now we said, okay, we did a little bit of derivation last time, and we came up with these expressions. The one in particular that we're going to use today is this one for the capacity when there's feedback. But this is an optimization problem, and it doesn't really allow us to come up with any sort of simple way of comparing what the result of that optimization problem is with, say, the previous capacity result that we had, which was when there is no feedback. So what we're going to do today, at the beginning of today, is compare this equation 22.38 with the other equation. Okay, the other thing which we had was this theorem, if you remember it. We didn't really prove it, but this, again, should be fairly straightforward to everybody, given what we know before, which is, again, it's one of these sort of achievability is identical. The achievability point is identical to the information capacity point. Namely, you can compute with unboundedly small probability of error up to the capacity, but there exists codes. It doesn't give you a code. Again, it's one of these existence proofs. It says there exists a code, at least one code that has this property, or at least I should say there exists a series of codes that has this property, but it doesn't give us one. And this is only one side of the theorem. This says that for any sequence of codes that has this property of the probability going to 0, then the rate can't exceed this value. And then the converse would say, well, if the rate doesn't exceed this value, then there exists a code that has that property, the probability of error going to 0. Okay, so we didn't prove this last time, but we stated the theorem, and we said that the proof was very similar. It uses Fano's inequality, which I think we went over a lot the last quarter. So I'm not going to do it this time. But Fano, you should still be aware of Fano. It's useful. The other thing we did is we proved this very simple matrix equality. So everybody stare at that for a minute. Not just the equality, we're not going to go with that. And then the other thing, which I think is very interesting, is that we can get these results, we can get results on non-negative definite matrices by using Gaussian entropy. And Gaussian entropy is really useful because we can use the properties of entropy and the monotonicity of the log to get results on things like determinants of non-negative definite matrices. The other result which we proved was this one. And so let's now continue on. So that's all review. So there's a couple more. So basically what we're going to do now is we're going to prove a couple of more matrix inequalities, and then, which like I said last time, are useful in their own right because they're useful matrix inequalities. And it's not necessarily the case that these are derivable only using information theoretic quantities, but they're oftentimes extraordinarily simply derived using information theoretic quantities. Like the one I mentioned last time again was the submodularity. Sorry, the submodularity of the log determinant function can be easily proven using the Gaussian entropy. So let's prove this one, because this is an interesting one. It's kind of like saying if you got non-negative definite matrices A and B, and you take some lambda between 0 and 1, then you have sort of this strange kind of multiplicative concavity going on up here. And it's multiplicative concavity, in fact, because when you take the log of it, this function becomes concave. In other words, the function, the log determinant, so it's a function of a matrix, and it's the log of the determinant is a concave function. Meaning if you take a mixture of log determinants, well, I should say a mixture of matrices, and you take the log determinant of it, which is on this side. Get some ink here. If I take a mixture of matrices and take the log determinant of it, that's going to be no less than the mixtures of the log determinants of the corresponding matrices using the corresponding same mixture coefficient.
They actually did this today in optimization.
Oh, they beat us. Darn those convex optimization people. And I thought we would be ahead of them. I'm very disappointed. Okay, we've got to go faster now. We have to speed up.
Well,
okay, all done. Any questions?
This proof will be better than the other proof.
Oh, will it? No, all right. Well, that's good. Okay, you're right. You're right. This proof will be much better than the proof. If the other thing is that this proof will be on YouTube. Was there a proof on YouTube? No. Actually, that's probably not true. Stephen Boyd tends to put a lot of his lectures, or he doesn't do it himself. He has lots of people do it for him. But a lot of his lectures are on YouTube. And it may very well be that one of his proofs of this quantity, this very quantity, is on YouTube. So. Now there's a challenge for Google. Can you search the YouTube video space for proofs of the concavity of log determinant? I bet it won't find it. Maybe it would. You should try it. And if it doesn't, then you can complain. But in any event, let's do this proof, because this proof is really simple. So we start off with, well, since, like first of all, note the theorem doesn't say anything about information theory. It's just a plain old vanilla theorem that you would see walking down the street, right? Nothing to do with information theory. So the first part of the proof also has nothing to do with the information. Say, okay, well, let's start off by taking two random variables, x and y, that are Gaussian distributed with covariance matrices A and B. And let's take a strange combination of these using indicators. So let's take an additional variable, a Bernoulli binary random variable, theta, which can take values 0 or 1 with some probability. Okay. And z is just this mixture, right? So if theta is 1, if theta is 1, then z gets x, and if theta is 0, then z gets y. And some additional assumptions, like, for example, these guys are independent, and theta is independent of both x and y. Okay. So is z Gaussian? Is this a mixture? Is this the same thing as saying lambda x plus 1 minus lambda y?
Do I need to do like an expected value or something? Or?
I'm just saying, if you take the marginal on z, is it Gaussian necessarily? Well, if lambda is 0, or if lambda is 1, it's Gaussian. What about when lambda is not 0 or 1? It's not necessarily going to be Gaussian. You can do all sorts of funky things. X and Y can have very different properties. Okay. Try it in MATLAB. Just you can do a simple simulation. It's going to look very non-Gaussian in certain cases. So it's not necessarily Gaussian, but that's okay. We know something about Gaussians. What do we know about Gaussians?
Maximum entropy.
Maximum entropy property. So maybe that's going to come in. So let's compute the covariance matrix of Z. First of all, so well, it's E of Z transpose, right? And and basically just plugging in the definition of Z into the expected value, where I'm using the squared in quotes. Just so you can see what that is. This is the official lazy man's version of writing something transpose. Okay. This is a very standard notation here. Everybody, people are going to think I'm serious. This is a very non-standard notation. But in any event, you know what that means. I'm just plugging in the value of z. And now I'm just expanding it. And so we've got 4 terms. We've got xx transpose times the indicator squared, that theta is equal to 1. And we've got yy transpose times the indicator squared, that theta is equal to 0. And then you have these other guys, this one and this one. So, except I've just made it such that you can't see them. So let's do them in a different color, like, for example, this one and this one. So what's going to happen to those guys? Yeah, they're going to be 0. Why?
Because it's indicator theta equals 1 times the indicator theta. So one of those is going to be 0.
That's right. It's always, everything for all values is going to be 0. So everything here, we can just cross off. Right? And so then what we're left with is, because theta is independent of x and theta is independent of y, we've just got the indicator squared, which is the indicator because it's 0 or 1. And so we just have lambda times a, which is xx transpose, the expected value, and 1 minus lambda times b. So the covariance matrix is the mixture of z, is the same as the covariance matrix of is the mixture of the covariance matrices of a and b, even though z is not Gaussian. So remember, non-Gaussian things have a covariance matrix too, right? They shouldn't be discounted from the property of having covariance matrices. Does that mean necessarily that it's the only property of those distributions? No, it means if they're non-Gaussian that they're also going to have non-zero higher order moments, and we know that Gaussians have 0 higher order moments, and Gaussians are characterized by the mean in the covariance matrix. Yep.
What is lambda equal to here in this derivation?
Lambda is just some value. It's the probability that theta is equal to 1. Remember, the theta was this this indicator variable from the previous slide.
And then?
So it's just a probability between 0 and 1.
Oh, because you're taking expected value of the indicator.
You're taking expected value with respect to x, y, and theta. Because remember, there's 3 random variables in here, right? There's x, this is random, y is random, and theta. So it's the expected value with respect. Whenever, this is just a general property. Like if you ever see an expected value of some complicated expression without saying what you're taking the expected value of, usually the convention is that you say, okay, well, where are the random variables? Well, capital X is a random variable, or y is lowercase, that's probably not random variable, but z is capital. I mean, but still people don't necessarily always universally follow those conventions, but whatever you're doing, when you're taking the expected value, it's find where the random variables are, and that's what you're taking the expected value of, unless you're saying like some sort of condition on something else. But in this particular case, what we're doing is we're taking the expected value with respect to all 3 of those variables. And so what we end up getting is that this form, so this is the 1/2 log of 2 pi e to the n of the mixture. This is the entropy of the Gaussian that does in fact have this covariance matrix is going to be greater than or equal to the entropy of z, because Gaussians have the maximum entropy for all distributions having the same covariance matrix. And we have conditioning reduces entropy, right? A linear form. And we have h of z given theta is, well, just if we expand that out, that's just equal to lambda h of x plus 1 minus lambda h of y. Right? That's just from the definition of conditional entropy. And so now we essentially we've about got it, right? Because that corresponds to this form of the mixture, this sort of multiplicative thing. Because when we can essentially, put the lambda and the 1 minus lambda up in the exponent of the corresponding ones, and that's the only thing that precludes us from combining them inside of the log. And then once we cancel out all terms, we've got this less than or equal to that. Okay, so again, that's very simple. Must we assume that x is independent of y? Doesn't seem so. So that seems superfluous. That's right. So you tell me now, how much simpler, on a scale of 1 to 10, how would you rate this proof? On a scale from 1 to 10, how would you rate that inferior, earlier, coffee-needed proof from the convex optimization class earlier today?
It's on a scale of complexity, right?
On a scale from 1 to 10. I don't know, you could say how much you like it. It could even be based on how pretty the font is, if you'd like.
The other one was on the whiteboard, so that...
Oh, well,
yeah.
Well then that's fine. You know, you just do it on the whiteboard.
Yeah, it's the way they did it there was with some.
Well, I just need the scale. I don't need the way they did it.
Yeah, I'd say this is a 3 in terms of low simplicity, and the other one's a 5, more complex.
Oh, 5 is pretty good, though. That's pretty good. So that was a 5er.
Yeah.
This is a 3er. Okay, so we are 2 better than that class. Because simplicity is the goal, right? I mean, simplicity but depth is our quest. But it's not always the case that we can achieve that. In any event, let's now make another definition. So this is something that the book calls causally related. The book calls causally related. It's the property. We're going to call it generatively factorizing, because I don't like to ascribe causal properties to directed models that aren't necessarily inherently causal. Causality is a very deep and rich topic that should be studied using methods much more sophisticated than just Bayesian networks or directed models or a particular order of factorization and conditional independence properties. But in any event, we're calling it factorizing generatively. And so remember, Z are the random variables corresponding to the noise, X are the random variables corresponding to the things that we're sending. And we're saying, okay, if there's a joint distribution associated with all of these guys, then it factorizes generatively if the following is whole. Now, first of all, we're saying, okay, well, f of z, the distribution of z, is not making any assumptions about it, so that can do anything we want. But what we are saying is that x, when we use the chain rule of probability, it's saying that x's are dependent on the preceding x's and also the preceding z's, but not on the future z's. So this is an assumption about the x's, not about the z's. Right, so the x's don't depend on future z's. But the thing is that because, if we had just gotten rid of that, if x was independent of z, sorry, for the YouTube listeners, if we'd just gotten rid of that and it was independent of the z's, this wouldn't be any assumptions about the distribution over x's, because again, this becomes the definition. This becomes just the chain rule of probability. So it really becomes an assumption about the relationship between the x's and the z's. In order to make this clear, let's use one of these graphical pictures again. So notice that, for example, x3 is dependent on z1 and z2, but there's no arrow going directly from z3 to x3, nor is there any arrow going this way. So those guys don't exist. Oops, only these ones going forward do. So that's an assumption. It's a factorization assumption. And it's a generative factorization assumption. At least that's what we're calling it. So if then the feedback codes, in fact the codes that we, the bigger picture that we saw earlier, that we explained, in fact satisfied this assumption. And so what this theorem says is that if this is true about the x's and the z's, namely that x's and z's factorize generatively in that fashion, without necessarily them being Gaussian, then the following is true. First of all, the entropy of the difference is greater than or equal to the entropy of z. Again, these kinds of things, like when you take additions and subtractions of random variables and you want to compare the entropy of that to, say, the entropy of something else, I think those are very, in general, non-trivial inequalities to establish. And in some sense, people are still looking at better ways of establishing them. There isn't, necessarily sort of the one best way of establishing them. And so in this particular case, we're taking the entropy of a difference, and we're saying the difference has no less entropy than the individual one. Now, on the one hand, you might think that seems counterintuitive, because why should a difference have more entropy than a singleton? But on the other hand, there's like random variables, and when you mix them, when you do things together in minus, subtracting them is kind of like a mixture. They can go negative, they can be more spread apart. Maybe it makes sense after all. Okay, then as a consequence, we've got this guy. And we can show that fairly readily based on what we know now. And this is just fairly straightforward information theoretic derivation again. So we have a chain rule property, which everyone should be familiar with at this point. We have a conditioning relationship by additionally. So what are we doing here? On the one hand, so remember, this is a difference of random variables. Now we're taking all of the random variables that are involved in this difference and just I guess brute force conditioning on them. And then we're adding an additional xi. So that's going to decrease the entropy. Or at least it's going to not increase it. And now that we're conditioning on all of the x's become a constant. And so the entropy is dependent on the entropy of z, which is here. It's conditional entropy. But thanks to the generative factorization assumption, if z has all of its preceding guys, it's conditionally independent of all of the x's. And that's something you can get. You can read that off of the Bayesian network picture that I just drew. Okay. Maybe that's not so obvious if you don't know about Bayesian networks, but you can actually derive it by looking at the factorization properties mathematically, or if you can read Bayesian networks, you just look at the picture and it just pops out. But we don't have the time. If you're interested in Bayesian networks, I strongly suggest you take a graphical models class. And then lastly, we've got the chain rule of mutual information, the chain rule of entropy, which gives us back that this is the entropy of z. So now we've essentially got it. So we've got this is greater than or equal to this. Okay.
You mentioned step 2 there, sort of brute force conditioning. What do you mean by brute force conditioning?
Well, I meant like if you have something like, where should we write this? Let's write it up here. You have like h of, let me turn off this stuff. H of a given b minus c. That's going to be what? Let's compare that with h of a given b and c. So which one do you think is going to be bigger or smaller? There's an inequality here that you should know at this point.
Seems like you have more information when you have B and C separately, so that one should be less than the...
Exactly right. Yeah. So this is the direction, because remember, functions of random variables only reduce information, and so we can derive this using. Does anyone remember? Data processing inequality. So the data processing inequality will allow us to derive this inequality. Or intuitively, you can say, okay, well, I've lost information. I mean, certainly in B and C, when I have them individually, it's sort of the brute force conditioning. That's why I was using that term. I mean, sort of brute force conditioning on B and C, we have all the information that's available within B minus C. But B minus C might have lost something. Right? Like suppose B and C are random variables that are dependent on each other. And in fact, they're deterministically related. So let's say that B is equal to C. So when I have B and C, that's the same as having either of them. But when I take B minus C, it's always identically 0. Even though B and C are both random, they're deterministically related to each other, so I'm conditioning on something that has no information, which is that it's always 0. So therefore I'm going to increase the entropy. That's an example. But then in this inequality we're also conditioning on xi. That's the other, we're additionally conditioning on that. So for two reasons that inequality holds, both because of the sort of so-called brute force property, which isn't really a property, it's just some words I just used in this context. And then secondly, because of this data processing inequality property, which we wrote at the top of the slide in red. Okay, so let's continue with this. So now we're going to assume that xz tilde vectors are Gaussians, and they have covariance matrices kx and kz. And we're going to let the factorization assumption hold. So we've got this, which is the entropy of some random variable, namely x tilde minus z tilde. Again, this is thanks to the covariance property. And now this is using the inequality that we just established. I mean, that the previous thing didn't require Gaussian activity. Here we're assuming it, so it doesn't violate it, certainly. And so this is this. And so basically then the results follow, because log, again, is monotonic. So it's an immediate consequence. Okay, so now we're going to start the depressing part of the feedback lectures. Namely, the depressing part of the feedback lectures is going to be one that says, at least in this particular case, feedback is not such a fantastic panacea that we've maybe perhaps expected it to be. At least in the context of this of the Gaussian channel and this particular type of memory, the Gaussian memory. Okay, so how many more bits per channel are we going to get from feedback? We're not going to have exactly the number, but we're going to have a bound. We're going to have a multiplicative bound and an additive bound, both. And both the multiplicative and the additive bound, as you will see, are not so encouraging. Because remember feedback, we said this last time, that in the memoryless case, the first thing you might expect when you're just learning about this is that feedback should help you a lot, right? And then eventually we realize, oh, feedback doesn't increase the capacity at all. And after you think about it, you say, oh yeah, I guess that makes sense. If I'm already coding at capacity, why should feedback help me? I already know essentially and have exploited everything about the channel, and there's no memory between uses of the channel, so how could feedback possibly help us? It already tells us what we already know. I understand. Now we're in this case, okay, well now there's memory. Okay, so feedback should really help us a lot. Right? But we're restricted because it's Gaussian memory. My memory is Gaussian. It's very fuzzy. Your memories are crisp, I'm sure. But Gaussian memory is not arbitrary memory. And Gaussian memory says the following, additively at least, that the feedback capacity is no greater than half bit over the regular capacity. Yeah, sad. Very sad. And I don't know, you could draw a tear. It's very, very sad. Tears of blood. It's blood, bit blood, bloods of bits. So how do we prove it? Well, here's our expression for the feedback capacity from before, which we turned into an optimization problem, but we're just sort of expressing the optimization problem. So now we're going to use the matrix inequality, this first one. Ky is equal to 2 to the n kx plus kz. And then we're going to take out the log of 2 to the n, and that's going to add us one more half of a bit. And that's equal to the 1/2 plus the non-feedback capacity. Done. So there's our additive bound on feedback capacity. Okay, what about the multiplicative capacity? So the multiplicative capacity says this, that you don't get more than a factor of 2. So by feedback. So equivalently, we've got this. I mean, this is here's the feedback capacity here, and here's the non-feedback capacity, and so we've got this additional factor of 2 here. So how does that work? We'll start with 1/2 of the feedback capacity, which, because of the extra 1/2, we can bring it up into the exponent of the numerator denominator inside of the log. We can add a numerator denominator of the determinant of kz raised to the 1/2 to both the numerator and the denominator. So theorem 22.3.4 gave us this bound on the concentration matrix, right? So it said, oh, well, kz is less than or equal to k of x minus z. Right? This was the bound we just proved. We used entropy to prove that. Okay. Next, theorem 22.3.1, which you'll remember, which is the concavity of the log of the determinant, but here we're using it in the non-log form, gives us, from this to this, gives us this inequality. And then lastly, we actually have to reach back into histories, the annals of EE515 to get from theorem 21.6.1. By the way, maybe you've noticed, but all theorems are numbered by the lecture number. So if we ever in the future refer to a theorem 6.1.8 or something, that means that that theorem and its proof are found in lecture 6. So this one means that it's found in lecture 21. And if you're wondering why I seem so smug about this, it's because it took me many a day fighting with LaTeX to figure out how to get this to work automatically. And so I like to point this out repeatedly to brag about how, yes, we now have automated theorem numbering by lecture in this class, in all my classes. But it's for your benefit. So well, you can find the theorem. But in any event, getting back to the topic, 21.6.1 was that very simple first matrix theorem that we proved last time. Actually, it is mentioned again in the beginning of this lecture, but we didn't prove it. But this is where the proof is, and that gives us this thing. And so, and then we're done. Okay. So then, combining the two theorems together, we get the Bilmes theorem, which is you take the minimum of both upper bounds to get the actual tighter upper bound. So feedback doesn't help us that much, again, at least in this case. Now that doesn't mean feedback isn't, again, the usual caveats. Feedback can make decoding a lot easier, it can make encoding a lot easier, and there could be many other types of memory besides Gaussian memory in a Gaussian channel. You could have a Gaussian channel where the noises are not Gaussianly related to each other, but
how exactly does feedback make decoding easier? Is it just simpler hardware implementation?
Yeah, well, I mean, suppose you get feedback, and again, the feedback is presumably perfect, right? So you know what you sent, and you get feedback, and you realize, wow, that's not what I sent at all. You can just resend it again. Imagine, it's just encoding and decoding is really easy, right? And human communication uses feedback. If I say to you, at least I try, we're using hopefully feedback, but that was feedback right now, this question. If I explain something to you, and you were to ask me the question, but why isn't 2 times 2 equal to 5? As feedback from the lecture material that I'm giving you now, that would be kind of like an error, right? I would be saying, okay, well, the channel is obviously very noisy here. I need to basically ask you to leave the classroom, right? So, no, I'm joking. But I mean, we use feedback in our discussions, and it actually helps conversations. And then when people nod and people say yeah and people repeat what you say, that kind of communicative feedback actually makes conversations and hopefully lectures. It makes it much more efficient. And that's one of the reasons why, you know, you guys are more used to being students than lecturers. I'm more used to being lecturers than students. But one of the reasons why we ask you, at least hopefully we ask you, are there any questions? And we look around, and if we see blank stares, it makes us not sure if what we're doing is worthwhile or is any good. And why, if you really want, you guys should collude together and go into a class and sort of all agree, everything he says we're going to be nodding the whole time, just to see how long it takes the lecturer to notice. But probably they may not notice because they're going to be so happy that what they're explaining is so well understood that their happiness is going to mask their logical brain to say, wait a second, this isn't exactly, this can't be right. So that's a very tangential answer to your question. In any event, this is a perfect time to take a break because we're now done with our feedback and Gaussian channels, and we're going to start talking about rate distortion. So, are there any other questions, or do you have any feedback? Everybody nod vociferously. No feedback? Don't worry, there's only a few more weeks, like 2.5 more months, or two more months of these ridiculous jokes. So you won't have to hear these much longer if you don't want to. But okay, no, seriously, are there any questions? No. Okay. Okay, so rate distortion theory. So this is a really important part of the lecture. So we're going to go a little bit slower today, just to make sure that we understand the intuition of this material. And this is because without having the intuition, the stuff that we're going to talk about in the next lecture or so is not going to make any sense at all. So first of all, just remember that when we talked about data compression, which we did, we said that there's this fundamental limit, which is the entropy. We have a random source, and if we want to compress without error, then we can do so as long as we don't compress down to below the entropy limit. And we have these two plots. And we saw these plots again in lecture 19 when we reminded you of them. And we also talked about communicating at the capacity limit. And we said that if we want to communicate without error over a noisy channel, we can do so as long as we don't exceed the capacity. So that's what these things explain. Now the question is, what if we want to compress below the entropy? Or if we want to communicate above the capacity? We know absolutely that we will have an error, right? This is an assured error. Now, if we allow errors to occur, we measure, rather than just whether or not there's an error, because I mean, to say that there's an error or not is one thing, but on the other hand, maybe if we could somehow measure the distortion and maybe bound the distortion in some sense, maybe that would be sufficient. And that would give us a nice trade-off in the sense that maybe we can compress below the entropy at some cost, and the cost is going to be essentially distortion. And the idea is that, you know, all errors aren't the same. All errors aren't created equally. Just because there's an error, the error might be in the lowest bit. We don't care. You know, if the error is in the highest bit, we obviously would care of a number. If the error is in the lowest bit, we probably, depending on the type of signal, wouldn't even notice it. And the Shannon's theorem says there's only going to be an error, but it doesn't say anything about where that error is or the nature of that error. And so with the distortion function, on the other hand, we actually can measure the nature of the error depending on the distortion function. Okay, so what we're going to do, and what we're going to derive, are generalized plots that look something like this. So if we have zero distortion, which is just this vertical axis, we're going to have this critical point here, which is the entropy again. Right? But now we actually have two axes. We have the distortion axis and the rate axis. And we're going to see that there are there's a region here which is achievable. So anything here is going to be possible to get. And then anything in this unachievable region will be impossible. So impossible in the same sense of that it was impossible to compress below the entropy without there being an error. What this is saying is that it's going to be impossible to compress at this rate, say at this particular rate here, with that particular distortion. So this rate and this distortion here are going to be unachievable. Okay. So let's set up the system and talk a little bit also about vector quantization. Now vector quantization, raise your hand if you've seen vector quantization before. Okay, so let's talk about it. So we've got a set of symbols, x, which is a random variable in an alphabet script x. And that could be a continuous or discrete domain. And if it's a discrete domain, then let's say it's a very big discrete domain. Like it could be a vector of integers, or it could be an integer with a very high cardinality set. And what we want to do is we want to quantize this space to x hat, where x hat, script x hat, is not too big. So in other words, if x is discrete, if it's a discrete random variable, then the big alphabet is going to be much bigger than the small alphabet. Okay. So here's an example. So like x on the left, script x on the left corresponds to a domain of possible values, and we could have lots and lots of different values. And on the right, we've sort of quantized it. We've essentially partitioned the space into a set of regions. And within each region, we have a representative, which is represented by these dots. Okay. And here in this particular case, we have x hat, script x hat corresponds to 7 regions, and the alphabet corresponds to 7 symbols that lie within the region. Okay. And so the size of the alphabet, the quantized alphabet, is going to be 7, which is going to be m. Remember, m was the number the letter that we used to represent the number of messages. And this is also, in this case, also going to correspond to the number of messages, or the codebook size. And these guys are going to correspond to our code words. And along with each code word, we have a region, RI, script RI. And the regions are disjoint, so we've partitioned the space into disjoint regions. Okay? Does everybody understand this picture? And this mapping from here, from this guy to this guy. Okay, good. So one thing that we assume is that the regions it's a covering, so it's a partition. When you partition into a set of regions, it's by definition, the partition is going to be covering. But just to state it, here, we're assuming that we're covering. So the union of the regions is equal to the original space. There are m regions, and then we have these representatives or exemplars. So within each region, there is some x which represents all elements within that region, and we're just going to, for region I, name that lowercase x hat I. Now we have an encoding function, which basically it maps from the domain x, so any value within x, and it maps to an integer. And we also have a decoding function, which is going to take an integer and map back to the corresponding representative in the ith region. So we're going to map from this big alphabet size, or possibly real numbers or real vectors, and the encoding function is just going to map it to one of m integers. And the decoding function is going to map it from one of these integers to the representative x hat. So then when we compose these functions, we take g of f of x, we're going to get x hat I, where I is the region index where x lives. Okay? So as long as it's the case that x is not equal to its representative, that means that we're going to experience some kind of loss. We're going to have distortion, right? Because we're not going to get back the same value. And we're just acknowledging that. We're saying, okay, well, I'm sorry, once we go through this encoding and decoding procedure, you're not going to get the goods that you gave us back. We're only going to give you a representative. It's very much like the US government, right? We vote people in and then we have representatives of us, which may or may not reflect our collective choice as a population. Sometimes there's quite a bit of distortion. So this is a quantization, right? So it's a quantization, and we have a code book. The representatives, the House of Representatives corresponds to the code book of the United States of America, right? So this is a code book. The set of representatives corresponds to a code book. And each X is a code word. Right? So the code words are the representatives of each region. Okay, everybody understand the setup so far? Now, how good is the codebook, or how bad is it? Well, that depends really a lot on what we want to do. You know, it might be really terrible. I mean, if we want to get back exactly the X's, and if the regions are big, and if the guy inside of each region is sort of not well representing all of the elements within that region, it could be very bad. But what we want really is a strategy for quantifying the quality. So this depends on these values. So how do we choose these values in a region? If we choose a value, like think about there being an underlying probability distribution. Like let's say that this is X, right? And let's say that here's one region and here's another region. It's bimodal within that region. So if we chose, say, this and this to be the representatives, those probably wouldn't be so good because these red marks correspond to where the probability is low. So it's not going to be a very, very good representation for, say, the more frequent X's that occur. Whereas if we did something differently, like for example, say, okay, well here's our representative and here's our representative, that's probably better because at least it's representative. It's representative of something that happens more frequently than not. But in any event, the values of these X's matter quite a bit to judge the quality. Number two, how many possible representatives are there? How many regions are there? Sorry. That's not correct. What I just said, this is really the probability distribution. So this is I guess what I said last time was really a combination of 1 and 2. So this is really the probability distribution P of X over X. Right? So within each region, what's the distribution of the values within each region? That's really what I mean to say here. And then thirdly, a measure of how bad it is to represent X by G of f of X. So it might be the case that, you know, having a little bit of distortion is not bad at all, in which case we could say this distortion is 0. You know, if I give a 3 and I come back with a 4, if that doesn't matter. I mean, if you win $3 trillion, and sorry, if you win $4 trillion and instead come back with $3 trillion, is that going to make your life any different? No.
Depends what the other people get.
Well, I'm only talking about you. Oh. You're right. It's a game. That's a good game theoretic response. But I guess it's really, you know, if you come back, if you have $3 trillion, your life is going to be the same. That's $4 trillion. On the other hand, if you have $3 versus $4, that's also going to be the same. But if you have $3,000 versus $4,000, that maybe could make a difference. So it depends. I mean, there's a distortion, and you want it. The other thing, I guess I should really add, what I wanted to say was for M, how big it is. If we have a very, very big M, we have more regions and we have more representatives. But that comes at some cost. So we have the expected distortion. So we have a probability distribution P of x, which is the distortion. And so here's a good example of this random variable. So where are the random variables here? So the random variable is really is x, right? So we're taking the expected value with respect to P of x, and it's the average distortion between x and its quantized representative. The quantized representation of x is given by g of f of x. Okay. Now, what does it mean to code? Well, the code is just essentially we quantize the space x of n. Oh, sorry. Sorry. Let me restate that. So what we've got now is a vector of x's rather than just one x. So here we're so far talking about x's, and I wasn't really saying whether or not it was a vector or not. Let's just say that now we've got n of these symbols from alphabet script x. And where the vector in vector quantization comes from is that what we're really wanting to do is quantize a vector and not just a scalar. So we have an n-dimensional vector which each element is a member of x. And so we can quantize this space into m joint regions. And the regions can be very arbitrarily shaped, potentially. So like in this case, let's say that n is equal to 2. So you could have one region that looks like this, and another region that looks like this. Another reason it looks like this. I mean, why would you want to do that? I don't know. But the point is that within the realm of possibilities lies these very strange, funny-looking regions. This probably would be called congressional districting, or gerrymandering, right? And so on and so forth. So we said that the House of Representatives was a code book for the population of the United States. How well things are represented corresponds partly to the shape of these regions, and one can create unmeasurable distortions by modifying the shapes of the regions. So we quantize this space into m disjoint regions, and again we're covering. Now each vector, each one of these x's corresponds to n source symbols. So this is going to correspond in some sense to our rates are going to be number of bits per source symbol again. So again, get used to or be familiar with the notion of a rate. We have n source symbols. And when we have a rate and we got of r, and we're using n source symbols, then we're going to have 2 to the nr, which is m possible messages. So m is going to be our index set. And rather than talking about m, we're really going to talk about the rate. So actually, let's go back to this slide and say, or rather, r, where m is equal to 2 to the nr. Right? So the r is our rate, because we're really talking about things in terms of rates. So here's the rate. Which is going to be positive. And so again, we can write the rate as so we have m messages or m exemplars or m, so it's log of n, so the number of bits needed to specify one of these indices divided by the number of symbols, that's the rate. It's the number of bits per source symbol. So hopefully everybody's very familiar with this at this point. And again, as the rate goes up, it should be possible to get the distortion down. Certainly as the rate goes up, is there ever a scenario where it makes sense that the rate could go up and the distortion would necessarily have to go up? Does that make any sense? No. You could always increase the rate, you could have more integers and just never use them. Just never map to them. So increasing the rate will never ever require the distortion to go up. It might not help, but it never, in the sense that it might not require the distortion to go down, but increasing the rate will never require the distortion to go up. Okay, so we have a source distribution, a bunch of these random samples from a distribution P of x, and we have usually n of them. An encoder function which basically takes a block of n of them and maps to one of the integers to the nr. So we're doing vector quantization, right? So we're quantizing a block of n of symbols together as opposed to each one individually. Just like what we did when we did compression, except that now what we're doing is we're mapping it to this integer, and the decoder doesn't map it back necessarily to the same alphabet symbol. The decoder, and in this particular case, we're again acknowledging the fact that we're mapping back to a different alphabet. We're mapping back to the alphabet where things are quantized. And it's a quantized vector, or a code word. So what we're doing is we're compressing to this index of integers, and then when we decompress, we must have the code book, and we just map things to the corresponding code book, or the dictionary. Sometimes you can call this a dictionary. Now, distortion function is some function that has domain the original alphabet x and input quantized alphabet and maps it to a non-negative real number. And it measures how bad the mapping is. It's a cost. You can think of it as a cost, as it says, well, how bad is it to represent x by x hat? We're going to assume that the distortion is bounded. So there's some finite value d max that bounds all distortion values, which is needed sometimes. One example is the Hamming distortion. So let's say that we're using it's a very simple distortion. This basically says that if it's equal, you get 0, and if it's not equal, you get 1. Right? That's bounded. If x is a bit, and you add up these things, and that corresponds to the Hamming distance. So this makes sense for bit strings. And in particular, when we take the expected value of the distortion, we get the probability of non-equality. Okay. But there are other possible distortions. There's like the squared error, which is x minus x hat, or the 2 norm, or p norm. Now these aren't bounded, right? But if we restrict x to be within a fixed range, like if x is guaranteed to be finite within a finite set, then these are bounded. Feedback. Like if the picture looked like this, then even the biggest difference between here and here would be finite. So now we can find an extended distortion. So when we take a block of length n, we just take the average distortion. So like this is what I said before, like if this is the Hamming distortion, we get the Hamming distance. Well, the Hamming distance is usually without the dividing by n. But in this particular case, we're dividing by n. And we can actually compute the average distortion of a code. So D, which is the distortion of a code, basically is the expected value with respect to the source symbol distribution P of x of the block of length x and the recovery g of n of f of n of x of the block. And you can just look at it by, we're just basically summing or integrating over all source symbol blocks of length n and computing the probability of that source symbol block of length n times the distortion. So let's just talk about the setting. So first of all, you should think of this more like compression than communication, or like channel communication. Because what we're doing really is we're trying to take a source symbol and represent it with a small number. What we're going to be doing is trying to represent it with a small number of bits, right? But we're going to accept a certain kind of distortion. So the rate of the code is in bits per source symbol. So if we want to compress, what do we want? We want basically small rates. Right? Small rates means better compression ratio. Right? Log m over n. Right? How many bits? We have m messages we want to send. We take log m number of bits and we divide by n for n symbols. If the rate is small, we're doing a pretty good job. Unlike communication, where we want the rate to be large. And at the same time, because now we're accepting distortion, what we'd like is, for example, a code that has the minimal amount of distortion. And we'd like to, for example, maybe think about possibilities. Like, does there exist a code that can compress at this rate and at this distortion? Can we prove Shannon-like theorems that says, if you compress at this rate and this distortion, there exists a code or there doesn't exist a code? Or, if you have this code that has this property, then it must be the case that the rate and distortion fall within some range. Those are the kinds of questions we want to ask, which are, fairly straightforward generalizations of what we've already done, except that we have always assumed that there's no distortion. We also have a code book. So the code book consists of these to the NR code words, which you can get at by just listing them or just using the decoder functions applied to the integers between 1 and 2 to the NR. Okay. And we have that each code word is a vector, an n-dimensional vector. And we can also refer to the assignment regions using like the inverse, the sort of function inverse-like notation where we say, okay, for the ith assignment regions, remember f of n was the encoding function. F of n was this thing that says, okay, for any of these x's, map it to its corresponding region. Now, which is an integer, the index of its region. But if we take f inverse n and apply it to an integer, it gives back the entire region. So this is really the same as this from before. The other thing to note is, again, because of the distortion and because these regions consist of more than just a single point, there's going to be more than one source string that maps to the same target string. So like when we have, there will be x and x prime that when we apply f and g to both x and x prime, or I should say, when we apply an f and g each to f, to x, and to x prime, we're going to get the same code word back. So if that doesn't make sense, so let's say here's two regions, and so both of these values are going to map back to the same code word here, which is green. Okay, that looks like an unhappy face again, doesn't it? But that's not meant to be an unhappy face. Okay, so here's our notion of achievability. So before we were talking about a given rate being achievable. Remember before we said that a rate is achievable if there exists a sequence of codes that has vanishing small probability of error. Like in the compression case, we said that a rate is achievable if there exists a sequence of codes such that as the block length gets big, this probability of error goes down to 0. And now we're saying a rate and a distortion together pair. The pair is achievable if there exists a sequence of codes at rate r, f and gn, that we're not asking for the probability of error to go to 0. All we're asking is for the distortion to eventually get below the prescripted distortion, the prescribed distortion. So D is the maximum allowable distortion. Are there any questions about this? Is everybody perfectly understanding this? Yeah.
Are there any restrictions on the distortion function you can use, like convex?
Not yet. I mean, the only thing is that it has to map to a non-negative value, real value. I mean, but again, we're just saying this is just a definition of achievability for a given distortion function. So achievability is defined with respect to a given distortion function. Right? It might be, you might have a sequence of codes which is achievable for one distortion function, and it's not achievable for another distortion function. So that really is in some sense a parameter to this definition. So great, we can make errors. We all make errors. To err is human, right? Now we can modify that and say to err is to code. So we're trying to make coding theory just like humans. But on the other hand, we can't make too many errors. And, you know, to err is human, but to make too many errors is, I'm not sure what that is. We can't make too many errors in life, can we? We can make errors, but if we make too many, we won't succeed as well as if we only make bounded numbers of errors.
Didn't you say the distortion function is bounded, so no matter what you do, you want the average distortion to be bounded?
We're bounding it by d. The distortion function has to have some d max, and d max could be much, much bigger than d. Right? So we're not saying anything, we're just saying that there's some maximum value within the range that distortion is. But here we're asking for a particular pair d and r, and d, cap D, could be much, much smaller than d max. So it's still sensible. But that's a good question. So obviously if d was bigger than d max, you know, that basically if d is bigger than d max, then what would the rate be in such case?
0.
Right. Because no matter what we do, we're never going to exceed that distortion. So when d is too big, we can compress down to 0 bits. Great, we've broken the Shannon barrier at a little bit of cost, namely 0 information, 0 communication, 0 fidelity, 0 knowledge. So basically it means we can make errors, but we can't make too many. We have to have bound distortion, and maybe the type of errors has to be of a particular sort. So not all errors are created equally. It might be that some errors are horrendously bad, and other errors are completely innocuous. So it depends on the distortion. So now the rate distortion region, we can talk about a region. So R and D can be seen in a two-dimensional space, right? The rate distortion region is the closure of the achievable rate distortion pair. So let's basically say we have, here's a rate, and here's a distortion, and say, okay, that's achievable, that's achievable, that's achievable, that's achievable, that's achievable. And we look at all these different achievable points, right? Something. And then we say, okay, we take the closure. So then the rate distortion region is going to be the closure of the achievable points. So it's a closed region. And we're going to see that now, we talked about last time that it says that if a particular point is achievable, we always, you know, if a particular rate and distortion pair is achievable, we can always increase the rate, right, by adding spurious bits. And we can always increase the distortion by adding spurious noise. So whenever whenever this is a point, the whole upper and right is achievable too. What's questionable is what's below it and to the right, to the left of it. So here's the rate distortion function. Rate distortion function is the infimum. So for a given distortion, the rate distortion function is the infimum of all achievable rates. And thanks to the closure property, it's a well-defined value because it's a closed region. So the limit exists. Or actually, not even that. We're taking the infimum. So even if it wasn't close, I take that back. The infimum breaks all closure barriers, doesn't it? Okay, so now a distortion rate function is just the inverse of that function. And basically, it's just the infimum of achievable distortions for a given rate. So hopefully this is understandable. Okay, the next definition is very important. Is everybody ready? I don't remember what it is, but the slide says it's very important, so let's all pay attention, including me. I wonder what it is. Should we find out? Okay, let's find out. Oh, this is very important. This is the information rate distortion function. Very similar to what we were talking about before. We're using the word information to mean that this function is the result of an optimization problem. We're going to talk a lot about this optimization problem in a second. But let's just remind everybody. So remember when we talked about the capacity of a channel? There were two notions of capacity. One was the result of an optimization problem where we take the max of P of the mutual information. And then we talked about the achievability and whether or not there exists a series of codes such that when the block length gets big, the probability goes to the error, and then basically the biggest rate such that that property is true. And that's the capacity function, and the other one, the optimization function, is the information capacity, and then we proved that these two things were identical. So what we did in this slide is we talked about sort of the infimum of achievability regions in this particular case. And now we're talking about an optimization problem. 22.45. So we don't have that they are identical yet, but as you can surmise, we are going to show them that they are. We're going to show that they are identical ultimately. Okay, so that's one thing I want to say about this. Two is that there's some underlying probability distribution P of x, so we don't get to control the probability of x. That's sort of given to us, and we don't get to control the distortion. So sort of distortion is given to us, and capital D is sort of a parameter of the function. And what the optimization problem says, zoom in on it a little bit, is to take the minimum over all conditional distributions such that when we take the expected value of the distortion function, so we're taking the expected value, so P of x is just the source distribution. We don't have control over that. What we're optimizing over is the second thing, is this guy. This is the argument of the optimization. Okay. So this is some joint distribution. It's P of x hat, but part of the distribution, the conditional part, is what we're optimizing over. The unconditional part, P of x, is just sort of a property of the source distribution. And so it's an expected value of this distortion here. And the constraint is that the expected value of that distortion, according to that source distribution, that the joint distribution that we're constructing, can't exceed cap D. And then the objective is the mutual information. And remember, the mutual information is governed by the joint distribution P of x hat, which happens to be equal to P of x hat given x. Okay, so this is the joint distribution that's also being used inside of this mutual information guy. Now I remember when I first looked at this, it seemed very confusing to me, which is one of the reasons why I wanted to go slow, just to sort of get an intuitive sense of this definition. And I don't even think, to be honest, and I shouldn't be saying this on YouTube, but I don't think that the book does a spectacularly nice job explaining the intuition behind this optimization problem. Because what we're saying is that this is a this is a compression rate. And we've seen optimizations in terms of the mutual information before in terms of the channel capacity. But there what we've done is we've maximized the mutual information. Here we're minimizing the mutual information. And then secondly, we have this distortion constraint. But first of all, before we get to the intuition, which I'll do on the next slide, let's just make sure that we completely understand what the optimization problem is. So what are we optimizing over? What are our choices? I mean, intuitively you could sort of think of this optimization as plugging in all possible conditional distributions into this mutual information expression. Well, first of all, checking before we've plugged it in, before we've even bothered to plug it into the mutual information. Let's consider all possible conditional distributions. Check if it satisfies the distortion constraint, and if it does, plug it into the mutual information, calculate the mutual information, and then store it, and then do that for all possible conditional distributions and find the minimum. Okay, any questions about just the mechanics of the optimization? Okay. So next what we're going to do after understanding the mechanics is getting some intuition of this function. So one thing to note is that when we, so p of x again is fixed. The source distribution p of x is not something we get to control. The mutual information function is convex in the conditional distribution, which was something we proved on date number 2 from last quarter. Check. So we are suddenly in the realm of convex optimization, which means that maybe that strange class you took earlier today is not so. I'm actually joking. I mean, of course, convex optimization is a class I think that everybody should take, and but this is nice because basically we've got now a convex optimization problem, and those of you, is everybody here in convex optimization? Most everybody? Sorry? Oh, you already took it. Okay, so this basically means that this sounds like a solvable prospect, even if it's perhaps analytically not solvable using, say, something like KKT or conditions or whatever. Certainly, this seems like something doable and computable. And in fact, the alternating minimization procedure is something that we will spend a little bit of time on, which was developed as a generalization of the Blehada-Aramoto procedure, which was developed specifically for computing this function. So we will address this. But that's good. Yeah, I already said that. Alternating minimization. The second thing is that it's, in some sense, related to lossless entropy compression. And you might think, well, why? Well, first of all, it's a mutual information function, and we know the mutual information is related to the entropy. But suppose for the moment that the distortion is 0. Okay, so we're insisting upon no distortion, and we're saying that the distortion function is non-negative. Okay, so the distortion can never be negative. Okay. So what we must have at the very least is that for all x and x hat that have positive support, namely that this is a possibility, so it's a possibility of going from x to x hat, we must have that the distortion is equal to 0. Since as soon as we have the distortion is not equal to 0 for x and x hats that have positive support, we're going to get a non-zero distortion. And let's consider a particularly stringent, strident form of distortion that basically says that if the distortion is 0, then we're equal. Just to get to the intuition of this. So it's basically a distortion that indicates error. Okay. So this would be one. In fact, two very simple ones. So the indicator of inequality, or even like the squared error. Squared error is going to be 0 if and only if they're identical to each other. Okay. So that means that for any x and x hat that have positive support by the probability, by the joint distribution, it must mean that x is equal to x hat when the distortion is equal to 0. This is still that assumption. Or in other words, the random variables are identical. Okay, if they have positive probability, They must be the same. Now, if the random variables are identical, we know that the mutual information between x and x hat is equal to the mutual information between x and x, which is the self-information, which is just equal to the entropy. So what are we doing in this minimization? We're finding an entropy. We're computing an entropy. And in fact, if the source distribution itself is uniform, then we're just going to get that the rate distortion function is equal to the entropy function. So, cool. So we've now related this to entropy. So in this particular case, we've said that if the distortion is 0, then the probability of error is going to be equal to 0. 0 probability of error. But that's not necessarily the case, is it, or is it not? So in general, does probability of error mean that the distortion is equal to 0? In general? So
does it depend on what the distortion function is?
Depends on what the distortion function is. But let's say that the distortion function has d of x and x hat equal to 0. Well, let's consider both of those cases. So in that case, does it?
Yes.
In that case. So in general, this is not true, but in the case when a 0 indicates identity, then it does. So this is as long as this is true. Now, on the other hand, does the distortion equaling 0 imply that the probability of error is 0?
No.
What if we also assume this? What if we assume this?
You'd have to assume stronger than that, right? You'd have to say.
So it means at dxx, like there's no other x that shifts the 0.
That's right, that's right. So in general, the answer to this question is no. And here's a simple example. Suppose that, and this isn't such an unreasonable distortion. Suppose it's, for example, the case that d of x hat is equal to the squared error minus some threshold. As long as the squared error is greater than the threshold, this is the distortion we get. So it's sort of like a squared error with a little bit of slack. It's like, or with a threshold. Saying, well, as long as it's not, I mean, it's kind of, we can even plot this. It sort of looks like this. So it's 0 for a while. There's tau. Something, or square root of tau, or whatever. But the point is that it's flat for a while, and then it starts going up quadratically. Right? So in such a case, we could have 0 distortion, but we're gonna have a ton of error, the flood of error, but it's all down in that region. So we're gonna have a very, very so it depends on a lot. So basically, 0 distortion does not imply 0 error. So this is getting back to this question. So the reason why we minimize the mutual information is that in some sense you can think of it as it's a compression at a particular rate in distortion, right? And you can think of it also as a communication. It's like a communication or a transmission from a system whereby we've got source symbols and target symbols of a different alphabet, but as long as the distortion is satisfied, we want to do the least amount of communication possible. So like when we do compression, you can think of compression as a form of communication where we're communicating from source symbols to their sort of compressed representation. in such a way that once we decode, there's going to be no distortion, right? The zero distortion case where there's this property of distortion. And that was the case when we got the mutual information between x and x hat, equaling the mutual information between x and x, which is equal to the entropy. But at the same time, we want, since that's the entropy, we want to communicate using the lowest rate possible. Because we're compressing. We're communicating to a storage device, or we're communicating to the input of a network. So we want the number of bits to be as small as possible. But now, since we're generalizing this to allow for there to be a distortion, we can minimize to below the entropy as long as the distortion doesn't exceed a certain value, which is in this case d. So to have a high compression rate, the rate needs to be low. So here's another sort of picture. So we're communicating from x to x hat. And you can think of it like as x might be an analog audio signal and x hat might be an MP3 file. Or x might be what you're seeing with your eyes and x hat might be an MP4 video file. It's lossy compression. And this is the analysis. This is the Shannon theory for lossy compression. Because we want to communicate to the receiver, which happens to be our lossily compressed format, a way that compresses as much as possible, which is the minimization of the mutual information, subject to that it's not distorted by too much. The ultimate lossy compression, if the distortion was unbounded, and we said that before with regard to d max. So like if we set d to equal to d max, then we can communicate at a rate of 0 because the constraint would never be active. So I've already said this, I think. I've already said this. And with the distortion constraint, that keeps us from compressing down to 0 bits. Because at some point, when we reach some point where we're going to be compressing so much that the distortion is going to exceed the constraint. The average distortion is going to exceed our constraint. Okay, so do people get the intuition of this? Any questions about it? So let's do an example. So Bernoulli random variables. So here's a specific form. So it's a Bernoulli random variable. It's a rate distortion function for Bernoulli with a distortion function which is just the indicator of equality. So it's the Hamming distortion. And the rate distortion function has the following form. So it says if the distortion is between 0 and the minimum of the two probabilities, P1 minus P, then the distortion has this guy, h of P, which is the probability distribution, entropy, minus h of D. But otherwise, if the distortion is greater than some value, it's going to be 0. And so when we plot this, it's going to look just like this bottom plot. I mean, it's already pretty big. Let's see if we zoom into it for a bit. So once the distortion is equal to P, which is down here, this is where I really need a pointer. Down here, we see that the rate is going to be 0. So at that distortion, we can achieve that distortion just by not setting any bits. Just by random bit flipping of a Bernoulli random variable, we'll have a distortion P already. On the other hand, if we insist upon having no distortion, then the rate has to be equal to the entropy. Because in this particular case, this distortion function is an indicator of inequality. Okay, so I think we're probably going to get removed from the room soon. So are there any questions? So again, to remind you that we don't have class on Monday because there's a holiday, so we'll be resuming next Wednesday. And this is unfortunately not the greatest time to stop because there's something I did want to say about this point here. but I think it would probably be a disservice to you to start it now and then get cut off in midway by people wanting to come in the room. So are there any questions? Let's just end with questions. No? Okay, I will see you on Wednesday. Do please start on the homework. Okay.
These guys are pretty quick to want to come.